Hello all, welcome to webinar SSCA webinar. In this video, we are going to see the presentation by Professor Mahesh Kumar Panda on his recent work, R optimal mixture design for a special cubic model. The paper is being accepted very recently in our journal Statistics and Applications, and it's being scheduled for publication in the forthcoming issue, volume 24, issue number 1. So, Professor Panda, congratulations on your publication. Without any delay, please go ahead.
Yes. So first of all, I am thankful to the journal committee for organizing such an initiative. Uh, Basically, this work is all about mixture experiment and optimality. So this R optimal design was proposed by Dete in 1997. The paper was published in Journal of Royal Statistical Society. So yes. So what is a mixture experiment? Mixture experiment is basically a special type of experimental design where the mixture's response depends upon the ingredient proportions, not on the amount of mixtures. One of the example we can consider fruit punch example, where there are three types of ingredients are there: watermelon, pineapple, and orange. And if you see the flavor of the mixture, it will depend only the percentage of the three ingredients: watermelon, pineapple, and orange. So due to this, that these proportions add to one, if you consider the simplex, basically that this ingredient will be fixed in q minus 1 dimensional simplex, and it will lose one of the dimension will be loose. So for example, whenever you are having good number of mixture components, then it will be a straight line, and when it is a three components are there, then it will be a triangle structure. So how do you actually understand these mixtures? If you see this x1 is equal to 100, it means that x1 is 100% present and the other mixture experiment, other ingredients are not there. On the other hand, if you see x2 is equal to 1, it means that the x2 is 100% present and the other ingredients are absent in the particular mixtures. How half 0? This tells you that the first two components are present in 50% and the third one is not at all present. So again, yes, so this is just a geometrical representation of the mixture experiment when q is equal to 3. So you can see that this watermelon, pineapple, and orange, these are represented by the vertices of the triangle, and the midpoints are basically when the scenario that 50% of the ingredients are present and the third one is absent. So there are two papers which have been highly cited in mixture experiment. One is SEFE 1958. Again, it is published in Journal of Royal Statistical Society. And this one is SEFE 1963. SEFE was the person who actually worked, he proposed the mixture experiment in the area of experimental design. So this is all about simplex central design. So it is one of the widely used mixture design where whenever the mixtures are present, they are in equal proportions. So example, you can see that here 100% one of the ingredient is present 100% and others are absent. The binary blends where you can see that 50% of the two ingredients are present. When you say tertiary blends, three ingredients are present and they are in equal percentage, that is 33.3%. So yes. This is a generalized version of simplex central design, where actually we are taking different type of barycentered points. Basically, barycentered points are what we define it in mixture experimental depth. So in this case, as only one ingredient is present, that is why the depth is 0. Whenever it is two components are present, then that would be 1. So here is a collection of different barycenter points and their weights basically. So these are arbitrary numbers R1, R2, R3, RQ, and we make sure that the total weight should be equal to 1. And this is all about the symmetric weighted central design. So what are the different mixture models are there in the mixture experiment? We are having surface canonical polynomial model, Baker's model, low contrast model, Tarot and Waller's additive model, K model for mixture experiment. And among all these models, the most widely used one is the second degree canonical polynomials proposed by SETI. The issue is whenever the response for basically is not a simple type of thing. For example, you can see this one is where actually it is a complex type of problem, curvature type of type. Then cubical canonical polynomial is a better choice as compared to the second degree canonical polynomial model. One of the more advantage of this cubic canonical polynomial is that it actually capture the nonlinear building effect, both synergistic and antagonistic effect, whenever you are having three components or more than three components. Now, review of literature with reference to the cubic model. If you see, Kiefer was the first person who worked on the D-optimal design. There are three different types of mixture model you can find in the literature: cubic model without three-way effect, and special cubic model. So he found the in 1961 Kiefer found D-optimal design when Q is equal to 3. Then it is Uranus in 1964 he obtained D-optimal design for the special cubic model when for the general Q component mixtures. Mikhail in 1989 D-optimal design he obtained for cubic model without a three-way effect for again general Q. And Mikhail in 93 he obtained the D-optimal design for the full cubic model when it contains Q number of components. Recently, Zhu Hao 2024 they obtained A-optimal designs for the special cubic model Q for the Q components mixture. And Panda 2024 he obtained the A-optimal design for cubic model without the three-way effect when the mixture contains Q number of components. So let us try to understand what is this different types of optimal design. Though I have only considered three types of design, we are having the alphabetical design like A-optimal, D-optimal, and A-optimal. So what is the A-optimal design does? Basically, it minimizes the trace of the inverse of the information matrix. So directly it tells you that it minimizes the average length of the principal axis of the confidence ellipsoid. D-optimal, it minimizes the volume of the confidence ellipsoid, and E-optimal, this minimizes the longest axis of the confidence ellipsoid. So as we know that in the experimental design setup, D-optimal design is the most widely used design. However, the issue is the D-optimal design. It is that whenever the number of parameters increases, the computation of D-optimal designs actually becomes a difficult task. And as an alternative, Delta 97 he suggested a new type of design known as R-optimal design. So what is the R-optimal design? It minimizes the product of the diagonal elements of the inverse of the information matrix. And in geometrical sense, it tells you that it reduces the joint confidence region associated with the conforming T intervals. So this is the ideal linear regression model setup. Eta x is equal to expected response is equal to fx into beta. Eta x denotes the expected response, fx is the model expansion of x, and beta is the factor of unknown parameters. Here we are assuming the errors are independent and identically distributed, having mean 0 and constant weighting sigma square. So this is a continuous design setup where we are taking s number of points, having the weights W1, W2, Ws, making sure that total weights is equal to 1. Then we can define the moment matrix or the information matrix as what? That sum over I goes from 1 to s weights into the model, and then transpose of it gives you the moment matrix of the information matrix. So what is the R-optimal design? Basically, it defines a design is said to be R-optimal if and only if this quadratic form, what you can see, is equal to exactly the number of parameters associated with the model f of x. And data 97 says that whenever the support points are the support points of the R-optimal design, equality will hold, and in the other points, if you take in the, then it will be a strictly less than B. So what is the main result? Yes, so you can see that this is the special cubic model where actually you can see that linear type of part is there. This is the quadratic part and this is the cubic part. And this exactly contain, if the mixture contain q number of components, then it exactly contain q into q square plus 5 divided by 6 number of parameters. So with reference to that, we have actually considered the simplex centroid design. And here the simplex centroid design is Q3. That means only we are considering the linear, the binary and tertiary. And rest of the centroid points, as you can see that the simplex centroid design, we need to only consider up to this J0, J1 and J2. We are not going to consider the rest of the points in this. So then it becomes a Q3 simplex centroid design. So in this case, yes, we have proved that the Q3 simplex centroid design is a R optimal design for this particular model, where we are associating. Yes, I find.
Yeah, please.
Yes. Yes, so we are here we are assigning the weights alpha 1, alpha 2 and alpha 3 to the vertices, binary mixtures and ternary mixtures. So yet, yes, in the paper we have derived for different values of q up to 3 to 18, we have derived this value, and also we have proved the equivalence theorem. So this is just a graphical picture where actually we are trying to see how the particular D and A optimal design perform with reference to R efficiency value. So here it is interesting to see that when you take from 3 to basically 11, there is one of the design, basically I think it is the D optimal design has higher R efficiency value, and when it crosses after 11, the A optimal design is performs better as compared to the D optimal design. So in this case, one can think of that if you are thinking of a dual optimal design, especially R optimal design is there, and either you are thinking of D or A, then you can go for what? For Q is equal to 3 to 11, you can think of D optimal design, which is actually your R efficiency value is very close to 1. And then later on, if you are thinking for 11 to 18, you can think of A optimal design as an alternative design which has higher efficiency value. Yes. So I have already explained the conclusion. And nowadays, basically in the optimal design setup, people are looking for either universal optimal design. Definitely that is better than all this design, or either you need to go for multi-objective, multi-optimal design setup. So it is basically here, it is a recommendation that whenever it is Q lies between 3 to 10, one can use D optimal design, and if it is 11 to 18, you can think of A optimal design. These are my references. Thank you.